we're going to be decompiling nav-mesh-h as an example for how to use the decompiler for Jack 2. So first we need to set up the decompiler config file to look at this file, like that. And then we should start looking at the all types file. So this is basically a list of all of the automatically detected types and functions and symbols in this file. And they're commented out by default because they're just guesses and they can be wrong or need some adjustment. So you have these def types that define types, and then at the bottom you have some define externs, which are defining symbols, which can be functions or global variables. And usually the first thing I do when decompiling is make all the types work. Sometimes you'll reach a type, you can't figure out what it means, so you leave it for later, but it's usually best to go through and figure out the ones you can, or at least make guesses before you start looking at the functions, because chances are the functions in this file are going to use these types. So first step is to just run the decompiler once and just make sure it's working on this file. There's a decomp2 script for Linux, and there's probably a task file to do this on Windows, I'm not sure. So we run it, get a whole bunch of warnings and errors about unknown symbol and not knowing types, but that's fine. Now we at least have some output to look at. And the output we usually look at when we're getting things working is this IR2 file, which is the intermediate representation of the decompiler. So for now we're not going to look at that, just going to fill out the types first, but we'll come back to this. So here's an example of a type, nav-mesh work debug. It's probably just some way for them to dump a bunch of vectors to one spot. Things look right, except for this sphere array here, which is some array of 16 unknown things, and it's located at an offset of 192. Because it's called sphere array, I'm going to guess it's full of spheres. Then the other thing we have to decide is, are these spheres, is it 16 references to spheres, or is it 16 actual spheres stored inside the type? And based on this size, I think they're going to be spheres stored inside the type. But pretending I didn't know that, let's say I guess wrong, I run the decompiler, and I get this error here which says the type came out to size 256 bytes, but the assert was set to 448. So the decompiler tells us, hey, you did something wrong, this type was supposed to be bigger than it was. And we know the correct size for every type because that's information that was stored in the game, and these asserts here basically throw an error if you get the size wrong. So I'll add an inline here, and oops, move all these over. And now the decompiler should be happy. Yeah, let's move on to the next one. So these unknowns, you can look at the spacing between these. So offset of 0 bytes, offset of 4 bytes. This should be something that's 1 byte, so we'll guess uint8. Could also be int8, but we don't know. Same here, and same here. And you'll notice that this is only 3, so why isn't this 11? Well, because uint32s have to be 4-byte aligned on the PS2. It can only do aligned reads, or aligned loads and stores, and the original compiler and our compiler both know to insert padding bytes to align stuff. We have another sphere array. Probably the same thing there. Let's check it. Got it right. This looks fine. Okay, here's an example of one where they must have messed around with the memory layout themselves, because they've got a bunch of fields that are located on top of each other. And this is a pretty common thing for them to do in places where they care about packing things or having some convenient way to access things with overlays. So this type is 64 bytes. So this is going to be some 1 byte thing. We'll guess UN8. Vertex, this guessed by decompiler, what it really means is that we found something called vertex in a type called nav-poly in Jack1, and we just copied it over. And this might have been right for Jack1, but in this case I think it's wrong for Jack2. I think this should be an array of 4 inline vectors, because then it'll overlay these. I don't think it makes sense that the X component of the first vertex is a bunch of UN8s in this case. So I'll change this and leave a note. That's not going to fit. And because all of these are overlaid of other types, the offset asserts will fail, because the compiler will try and lay these out, to not overlap. So to fix that error, we just remove the assert and basically say hard code all these offsets. And we're basically, telling it we know that these are manually set. For instance, let's see. Yeah, like these UN8s are hiding inside of the W component of this vector, which is a pretty common thing. Usually like the XYZ is used for floats, and then they stuff a bunch of flags in W. Up here we have another example of something going wrong with the decompiler. This class is a child of vector, and when we originally generated this file, vector was broken. So all these fields here already exist in vector and are now duplicated. So if we go and decompile this, it'll give us an error about hey, this already has something called data. Type nav vertex already has a field named data. And you get this whenever you're a child of a class that didn't work for whatever reason, so we just have to delete these manually. I know all these fields are in vector. We could go back and look at the definition for vector and we'd see all of these exactly. So we can just safely delete them because this is a child. And now it should work. It does. Nav sphere, I don't know what that is, but looks fine. 16 bytes, sphere is 16 bytes. Nav ray, everything looks good. These came from Jack1, but they seem reasonable. These are probably like true or false. Here's another example where it's wrong by default. We just look at the error message we get. It says, hey, next poly was placed at 8, but offset assert was set to 32. That was next poly. So basically each of these is a reference to nav vertex, takes 4 bytes. So then nav poly would get placed at 8. That's wrong. These should probably be inline. And if these are 16 bytes each, then this one goes at 32 like we expect. And let's see that. And those are 16, so that makes sense. That worked. Another one for Jack2 is if you think it's going to be a Boolean, you should probably just change it to symbol instead of basic, because symbols are no longer basics in Jack2. That's going to be really annoying. Clamped travel vector to mesh return info. That's a long name. But the type looks good. Okay, and here's one where it totally failed to read any of the fields, so we have to go read them manually. So we should look for the inspect method. It will be method 3 of nav-mesh. And it still did manage to read the flags, so we'll get some confirmation that we have like the right size in total, but we just have to copy these and not make any mistakes. And to verify it, we can go look at the decompiled inspect method later once it's all working. But this is a child of basic, which means that there's a 4-byte offset applied to the pointer that's passed around to represent this. So the beginning of this type is stored at the reference minus 4 bytes. And the first field in a basic is always a type. So this code here, this first block, is actually going to be accessing the type and printing out the type. So I should probably explain what this is first. So each function starts with a header like this. If it's a method, it has a name like this, where this is an ID number and this is the type. The ID numbers have from 0 through 9 are sort of fixed, and they always mean the same thing. 0 is new, 2 is print, and 3 is inspect. So this is the inspect method for nav-mesh, and it basically prints out the name and value of each field in the type, which is super useful for trying to figure out what it does. And it starts by printing out the name of the type. On the left is the MIPS assembly, and on the right is sort of a beginning of decompiler output. In this case, it's told us there's a warning, and we don't know the type of this function at all, so it can't really do much, but it gives us at least some intermediate output we can look at. So this is loading the format function to the T9 register. Format is like their version of printf. This is getting the value of the true symbol. If you use format with an argument of true, it prints it to like a standard output type thing. This is loading a string into an argument register, right? So A0, argument 0, A1, argument 1. And it'll show you what the string is here. So this will get replaced with the address. This will get replaced with the name of the type. So then the next argument register is the address of the nav mesh, and you can see this GP ends up being set to A0, which was the first argument into this method. So that makes sense. And then this is grabbing the type from the basic, which is the first thing in the basic, but because of the 4-byte offset, there's a -4. And then we call the function, and then this is printed. And then this process sort of repeats for every single other field in the thing that we're going to have to go through. Maybe I'll skip some of them, but we can do work, nav, mesh, work, and we can see it's loaded from an offset of 0 plus 4, so we should put an offset assert 4, and that'll check to make sure that we've understood the basic offset correctly. And we get an error that size came out to 8, but the size should have been 112, which is fine. We only added one field out of many, but we didn't get an error saying that the offset was wrong, so that's a good sign. Like if I got this, if I just put 6 here, right, because I used the wrong number, it would tell me field was placed at 4, but this offset assert was set to 6. So this is a nice way to check that you've done it correctly. Poly array, unit 32, and these are all like, I'm just looking at these numbers here, right? It's like a, this is load word unsigned, which is 4 bytes. This has an offset of 4, so the automatic layout will be correct here. We don't need to bother with the offset assert because we're pretty sure it's just going to be right. Static sphere count, that's in uint 8. For most of these, there's not much information we can put. I guess poly hash here is printed with this A, which usually uses basic or something like that, a symbol, which is weird. I would have thought this would be a number or something, but whatever. And then these are just like addresses or uint 32s or something like that. They might be pointer, but we can change this later. Just make sure we haven't gotten off. We'll add an offset assert here, 28 plus 4-byte offset is 32. And we get the size error but no offset error, so we're good. And here we've got some sphere. We're no longer doing a load, we're doing an add, so it should be inline. And I'll inside the offset assert, just make sure I got this right. 44 plus 4 is 48. And this origin vector is also inline and it's placed directly on top of that, so we're going to need to manually set its offset. Entity is probably going to be an entity, we'll just set that. And then this is why it didn't work. It's got this code to print out some sort of enum or bit field here, nav-mesh flag. This is kind of weird. It looks like there's only a single thing, like bit 1 is dummy. This is a really weird one, but you can add it anyway. Basically, enums have to be added manually. You have to give them a type. This is loaded with LBU, load by unsigned, so it should be uint8, and it's bit field, and it has one entry which is called dummy, and it's bit 0, right? Yeah, so this code is saying load the value. If the value and 1 is non-zero, or is equal to 1 rather, then print out dummy, and that's it. Usually there'll be a ton more cases of these. We got lucky, and this one's pretty short. Then we got pad 2, and because these offsets are 2 apart, I'm going to guess the pad is, sorry, pad 1, uint8, and there's going to be 2 of them. Nearest threshold, and this prints out in meters like this, so type meters. Let's check that we haven't gotten off. Water max height meters. And another pad 7. Yeah, still get a size error, but no offset errors. That's good. I don't know what size it should be, so I'm going to guess and check. 91 should be 112. Should be uint 32, right? Yep. Okay, so we figured that out. Hopefully this doesn't happen too often. Usually these should be already filled out for the most part. So now we're going to look at the code here and figure out the functions that aren't there. So I'll start with this one. This is vector normalize unity. So this is probably something that finds the length of a vector and divides everything by that length. So just looking through it real quick, you know, this is loading some floating point constant. You can sort of recognize this. I think this is floating point 1. Puts in a floating point register. It's loading 4 floats from this address. So these VF registers each store 4 floats. So V0, which is set to the first argument, 0th argument, which is probably a vector. And we do a multiply, okay, square everything, or XYZ. That's kind of weird, why do we do that? Go back and forth, whatever, this is just goal being dumb. Then we put 1 into VF3 here. These 3 multiply adds with VF0 are basically, I think, adding together the X, Y, Z component of VF2 and storing them in W, and then take square root. So this is just doing vector length, and then r square root, it's like 1 over the square root, and then multiply. So this is, yeah, it's just normalizing a vector. I don't know why they have another function for it, but they do. And it seems to normalize a vector in place, which I guess is different from the normal function. So we'll go over to the all types file and put in our guess for the type. So we think that there's just going to be the input is a vector, the output is a vector. It just returns the same vector, right? So this V0 register is also the return register. Oops. So let's try it. And yeah, this looks fine. You know, there's some weird moves going on here, like this 1.0 goes all over the place. But that looks right. Well, this looks very similar, but it's called copy, so, and I see it using argument 1 to load from, so I think it's just the same thing, but the input and output vectors can be different. Yeah, literally it's the same thing, but there's just this line here. Alright, next is init array. Cool thing here is that we actually did this function in Jack 1, and there's the leftover type there, so we can try that one again. Yeah, this looks fine. It's interesting. It's kind of annoying though that this is using this code here, because there's another function called vector length that's also in line that computes exactly the same thing that the decompiler does know how to recognize, but this one is slightly different, so it doesn't work, and you get this ugly thing showing up. That's fine. Probably not going to use it too much outside of nav-mesh. Okay, this one is totally new, so we're going to have to do some guessing to figure it out. Point poly intersection. So one thing you can try just for fun is just, well, it's got a question mark, it probably returns true or false. Yeah, there's some like true or false thing here. So function return type symbol. Just run it and see what we get. So it already tells us, looks like there should be 4 arguments, and it's already sort of telling us what the problems are. So we load a 32-bit unsigned value from something with an offset of 0. It looks like that's most of the only time we use this. Yeah, that is, because we overwrite it here. So we should go and look at these types. So I think it could be a nav mesh, and this could be loading the work. Then we would have v1 as the work, and then we'd be indexing into work. Does work start with an array? Where's work? It does. And it starts with an array of int 8s, so that's promising. So I think the first argument is probably nav mesh work, because I see this load here. I see this, which is some like array indexing for bytes. I see that it comes from loading something at an offset of 0, so let's put that in. Although the weird thing is you'd expect this to be a method of nav mesh instead. But who knows. Okay, next A1. A1 we load from offset of 0, offset of 8, and that's it. So I'm going to guess this is a vector. And they're loading x and z, which are the sort of, the xz plane is the plane where this nav mesh stuff usually happens on, so that makes sense. And we expect there to be a point as an input because it's called point poly intersection. Next is A2. A2 is just used in a comparison operation, so it's some integer. I guess int. Next, A3. A3 is some array, and the fact that this shift operation appears before it, right, so this is some sort of like index into an array of something with a stride of 16 bytes. And then this T1 also seems like it's used like a vector. So something like inline array vector is probably a good guess for this one. Let's try it. Alright, well there's no errors up here, so that's a good sign. So I guess just to back up, what I expect this function to be doing is to look at each edge in the polygon and check which side this point is on. If it's on the inside for all of them, return true. If it ever figures out it's on the outside of any of them, return false. And to figure that out, they're basically doing like a 2D dot product and looking at the sign. So that all looks right. This looks a little funky. Right, so this is saying like add these two pointers together and then cast it to another pointer type. What's going on? Why isn't that working? So it's trying to read from this vertex table. Don't remember what that was. Oops. Oh, we guessed this was uint 8, but we were probably wrong. B should be int 8. Alright, so this is probably using LB. Yep, LB. I should have caught that. Much better. Okay, I think this makes sense. Go on to the next one, method 37. So this one's a method. You always know in methods that A0 is going to be type nav-mesh. Whatever type it is there, which you can just put in the decompiler as type like that. And you know, if you never know, if you have no idea what to put, you can just put object. Like we know it's 3 arguments, and we just put object for next to. And you can just try that and see what it says. It'll tell you like where to look for clues, right? So failed type prop at 2. This means operation 2. With these sort of operation indices. And this is looking at loading an unsigned byte at an offset of 14. So we should go back and look at these types and see if that makes sense for any of these. Nope. Maybe this. No. Yes, nav poly, that makes sense. No. No. And no. So let's guess that this is a nav poly. And it complains at 24. V1 gets set to A2. And I think it's just a vector, right? It's loading X and Z from it there and there. Oh, and then it complains, has return type of none, but the expression builder found a return statement. Yeah, so I see V0 getting set to true or false. And those are the only possible things, so it should return symbol. So now it looks kind of bad. So I don't like these lines because they're doing pointer adds. Then immediately after it, we're doing this weird like load float thing. So this L.f is sort of like I couldn't figure out how to decompile this, so I was just loading a float from this address. That's always bad. So what is this doing? This is looking at arg0 data, which is nav poly data. Is there anything else there? Okay, yeah, data is just a stupid, like, byte array that overlays everything. We don't like that. I just put score -1, which says prefer any of these things over it, if possible. And then hopefully these L.Fs will start loading from these vectors here. Yeah, that looks better. And then the only cast left is this int thing, which unfortunately I think is just sort of how this decompiler treats casts from int to uint. You know, like this is like a loop iteration variable. Darn. Okay, method 39. So already, look, we see this load byte unsigned from 14. Probably that means that S5 here is a nav poly. That's A1. So we already figured something out. This is just the same offset from the last method. Type nav poly vector. Oh, we should probably name that other method. Let's go back and name that other method first, sorry. This is doing essentially the same thing as point poly intersection. Right? Like it's the same thing there, and the same check, less than 0 return false. Sorry, greater than 0 return false. I hate this way that these comparison operations work. This is probably something like point and poly. This one was kind of weird because it let you specify the vertices as sort of a separate argument. And this one does the same thing, but instead uses this vertex table. Weird. It's 39. We guessed that, made a random guess sort of that A2 was vector. And we store a quad word into it, so that's a good guess. At 39, it's unhappy with. Oh, so this is using stack variables, kind of annoying. Getting something out of here. Jeez, what is going on here? So I think this is a case where it's using both stack structures and spilling stuff to the stack. And as a result, it's not having a good time figuring out what this stack structure is. And it also is probably unhappy about this one not being around. This one's a little harder. Well, based on this, I think A3 is also a vector. Let's try again with that. Yeah, let's tell it what this stack type is. You know, I'm gonna guess this is just vector. We should check. That's a big number. There's also some weird stuff going on here where SP56 is not really working as a float super well here. I'm going to leave this one for now. I think it's correct other than this line. No idea what it does, but I'll do that one later. That's probably a decompiler fix. And here's another one, 41. Let's just start with type. I think that A3 should be a vector. S2 should probably be a nav poly. S2, 3. Or sorry, S4. A1. I should have just guessed it. Yeah, it doesn't look like stack spills and stack guessing work together. I bet you there's a bug where I'm dropping a tag to decompiler. And then from here, this store quad is bad. But I see this guy, arg1 object, should be vector. Same problem with the float here. I'll leave this one too. Oh, this is a long one. Method 16. See a bunch of stack stores. It is looking at A1 plus 48. And at 32 there's a float. At 48 there's a nav poly. So I think this is nav ray, right? So this 48 here grabs this nav poly here, and then this is loading that vertex table byte thing that we've seen a bunch. I don't know why these are so full of stack spills. Yeah, I should probably read through this more carefully and come up with names for these, but nobody cares too much about the nav stuff anyway, so maybe not. And then we can go through and look at all the other stuff in the debug segment. These are all just the inspect functions, so I'm going kind of quickly. They're all good already. I do think they have some custom ones here. Debug validate current poly. That function doesn't do anything. Just returns false. Nav sphere from cam. Looks like it doesn't take any arguments. you can tell it doesn't take any arguments because it immediately calls a function. So maybe camera pause takes an argument. It does not. And the argument registers get overwritten during a function call, so we know that they can't possibly be used here. We know it doesn't return anything because it returns 0 here, which is what the compiler inserts when there's no return value. Cool, yeah, I guess that prints something. And now that we're done, nav-mesh-h, we can look at the output, which is called disassembly. It's sort of the wrong name, but I haven't changed it in a while. And this is the output. And it's got those weird FPR things that I've got to fix in the decompiler, but hopefully these will be fixed and they will never come back again.